guys, this is Andrew with HKN, and today I have a problem for you that is for ECE 3101, which is Signals and Systems. And today we're going to talk about Fourier Series. And so Fourier Series are ways that we can express periodic functions. Periodic functions like this guy here, which is 1 for 5 seconds, -1 for the next 5 seconds, and then repeats. So that's periodic. You know it has a function between two over a period, and then it repeats it to negative and to positive infinity. And so the idea of Fourier series is a lot like the idea of Taylor series. So if we had a function like this, right, we know that with a Taylor series, we can approximate it with a shift up and down, followed by a line, and then followed by a parabola, and then followed by an x cubed. And we would just keep adding these ad infinitum, and we would end up converging to this function within a certain range. And so that certain range is usually very, very close to the center here. So it's usually somewhere in here for Fourier series. For Taylor series. Usually between 1 and -1, or depending on how you work with x. It could be higher, but there's a radius of convergence for it. Nicely for Fourier series is they have a special type of convergence, but we say that they converge in value at least for all points on the period. And instead of summing up a bunch of different powers of x, what we say is we sum up a bunch of the different periodic functions. And the periodic functions that we know are sine and cosine. So, instead of writing the form like this, we write the form of a Fourier series as some constant a0 plus the summation from n equals 1 to infinity of a sub n of cosine omega 0 nt plus b sub n sine of omega 0 nt. And so something very special about this is that we can express any periodic function as the sum of a bunch of cosines and sines, and then a constant shift. And not only just a sum of cosines and sines, but sum of cosines and sines that are of multiples of the same frequency. So, and this omega 0 here is just, omega 0 is 2 pi over the period of our periodic function. So, in the case of our specific one that we're doing today, it would be 2 pi over 10, which is pi over 5. So that's something we're going to want to remember. But what this is basically telling us is that if we sum a bunch of cosines of multiples of the base frequency omega 0, then what we end up with is this wave. And the tricky thing here is we need to calculate our coefficients. These are called the Fourier series coefficients, and once we get them, we kind of just plug and chug. A0 here is called the DC term, and the reason it's called that is because it's like our DC current. It will shift our function up or down. AN is the cosine term, and BN is the sine term. And the formulas for these are that A0 is the average value of the function over a single period. So you just take the integral, divide by the length of the period, the integral over a period, divide by the length of a period, and you get A0. For the other ones, you do something very similar, except this one's actually half of a period that you're going to divide by out front, because the other one is going to be the other half. So we weight them evenly. And it's the integral over a period of the function times cosine omega 0 nt dt. And Bn, if you can have some reasoning, should be 2 over t, the integral over a period of f of t sine omega 0 nt dt. So if we can carry out these integrals, then we get a general an term, a general bn term, and our dc term a0. And if we do that, we should be able to get what our Fourier series representation of f of t here is for all time. So we're going to take a second to erase. So for this function up here, what we want to do is we want to calculate these Fourier series coefficients. So let's start with an easy one. Let's start with the dc term. So this function looks like, for half the time it's 1, and for half the time it's -1. So it looks like the average value is 0. And in fact, if you take 1 over 10, the period, and integrate from 0 to 10, f of t, where f of t is this function, you do in fact get 0. So we have no dc term of this function. Next we need to do is we need to calculate a sub n. And so this is the term for the cosines. And so we're going to prove it right now, but what we should find, and I hope that this makes some intuitive sense to you, is that we know that cosine and sines are orthogonal to each other, which means that that the influence from one does not affect the other. But also, it means that one is even symmetric and the other is odd symmetric, which means, for everybody else who doesn't know, if something is odd symmetric, if you have something like that where you have y cubed, where f of x is equal to negative f of negative x, and something is even symmetric if you have something like a parabola, where you have f of x is equal to f of negative x. And you can express any function, f of x, as the sum of its odd parts, so f odd of x, and its even parts, f even of x. So that's also where the periodic function representation for Fourier series comes from. That sine is even symmetric and cosine is odd symmetric. So this guy here is odd symmetric. So it should have, so its actual its actual representation is only its odd component. So all of the even components should be 0. So what that tells us is that everything in front of the cosine here should be 0, which means that our an term here should be 0. But let's carry out the integration to make sure of that. So we get 2 over 10, which I will make 1/5 at the end. The integral from 0 to 10 of, it should be f of t cosine of, we know that omega 0 is pi by 5, nt dt. And so this is a discontinuous function, so that means we have to split this up over the interval. So this is going to equal to, I'll make that simplification for 1/5 now, the integral from 0 to 5 of cosine, because f of t is 1 here, pi over 5, n t dt, plus 1 over 5, the integral from 5 to 10 of negative cosine, pi over 5, nt dt. And so we want to, so luckily this is the same integration except for a negative. So we know that the integral of cosine of omega 0 t is 1 over omega 0 sine omega 0 t. So what we get here is we get 1 over 5, and then the omega 0 is this guy here. So we get 5 over pi n. So these 5s are going to cancel. I will do that later. Then we end up with sine of pi over 5 nt. And here we're just going to get the negative of this, 1 over 5, 5 over n pi, sine of pi over 5 nt. And we need to evaluate these from 0 to 5, and this guy from 5 to 10. So cancel the 5s. So we just end up with a 1 over n pi that we can pull out front. And so if we plug in 5 to this here, we get sine of n pi. And if we subtract off 0, we'll get sine of 0, which is 0, so we don't need to subtract anything off. Over here, we get a 1 over n pi. And what we find here is that if we plug in 5, we get sine n pi, and if we plug in 10, we get sine 2 pi n. So we know that we have sine 2 pi n minus sine pi n. But what we know is that n can only be an integer, right? This n here is the index for the summation. So that means that an n can only be an integer in here. And sine of any multiple of pi is going to be 0. So that makes this sine n pi 0. It makes this sine n 2 pi 0. It makes this sine pi n 0. So everything here is multiplied by a 0. So in the end, in fact, what we do get is that we have no term for cosine in our Fourier series representation, which makes sense from our reasoning with odd and even functions. So now all we have to do is calculate what Bn is going to be. Bn, the general term, is 2 over 10, 10 being the period. And I'm going to split up the integral from 0 to 10 right away into 0 to 5 of f of t being 1 here, of sine pi by 5 nt dt plus 2 over 10, the integral from 5 to 10 of negative sine of pi by 5 nt dt. So let's carry out this integration. We're going to end up with something very similar out front. We're going to end up with 1 over n pi here. And so when we integrate a sine, we end up with a negative cosine. So we have a negative 1 out there, and we're going to use cosine of pi over 5 nt. And we need to evaluate this from 0 to 5. And then over here, we're going to have another 1 over n pi. And we're going to have a negative, the integral of negative sine is actually positive cosine. So we end up with cosine here of pi by 5 nt. And we need to evaluate this one from 5 to 10. So if we plug in 5 here, we get cosine n pi. So we're ending up with negative cosine n pi over n pi. And if we plug in 0, we end up with 1. So we're going to subtract off a negative 1, which means we get plus 1. And then over here, what we're going to end up with is we end up with, if we plug in 10, we get a 1 again. So we're going to get plus 1. And if we end up with a subtraction, I guess this would also be over pi n. Apologies for that. And this would also be over pi n. And if we plug in 5 here, we get this value, which is, but we're actually going to end up with a positive version of that value. So we should end up with cosine n pi over n pi. Sorry about that, guys. This should actually be a negative because we're evaluating the bottom limit. This needs to have a negative out in front of it. Okay, so now this is correct. So now we have the ability to combine terms here. And so if we do so, we end up with 2 minus 2 cosine pi n over pi n. And so this kind of looks like we're done. But there's actually some simplification we can make with the idea that this is that n is also an integer. So whenever we have a multiple of pi in cosine, if n is an even number, we end up with cosine of 0, cosine of 2 pi, cosine of 4 pi, and all of those numbers are 1. And so if we plug that in here, we would get 2 minus 2, and this would evaluate to 0. And if we plug in an odd number for n, we have cosine of pi, 3 pi, 5 pi, and those all evaluate to -1. And so if we plug that in here, we're going to get a 4. So actually, the simplification we're going to make is that cosine of n pi alternates between 1 and -1. Or what we can say it is -1 to the n. So what we have here is 2 minus 2 times -1 to the n over n pi, which is finally 4 over pi n when n is odd. Pull them on screen. No, so this would be for n odd. Wow, just barely off screen. So the top one is for n odd, and it's 0 for n even. So that means that we have our Bn. Our Bn is 4 pi over n when n is odd, and 0 when n is even. So with all that said, we can finally write what our Fourier series is. So recalling that a0 is 0 and an is n, all of our a components are 0. We can write f of t as it would be a0, but a0 is 0. It would be the sum from n equals 0 to, or 1, apologies, 1 to infinity of an, it would be an cosine, but we know all of our an's are 0, so there's no reason to write that. Bn, where this is 4 over pi n, times the cosine of pi over 5 nt. So we can exactly write this as a sum of the multiplication of these, but there's one more caveat we have to make here. It's 0 when n is odd. So we just say n equal to 1 and odd. And that's the way to write it. And this is actually a mathematical definition for this function if we take it to infinity. It will converge exactly in value. And so to show you that, we have a little MatLab tutorial here. So what we're going to show you is that instead of taking it to infinity, if we take it to infinity, if we take it to a really, really high number, you should see it start to converge. So I've written a script for this, and I'll take a brief second to explain what the script does. So you see that I've defined n, and n is the number that we're going to take to up here. We can't take infinite summations. We don't have the time for that. So that means that we can only take a certain number, and so we're just going to see what it looks like as we take bigger and bigger numbers. That is our base frequency, pi over 5. T is the time axis, and f, which is the function that we're going to create here, is created by taking a summation inside of a for loop from 1 up to n, but we're going by 2 because we only want the odd numbers. So that's what the 2 in the center of the colons mean. We calculate an, and then we add on the term to f. So each time we're adding on the next term to f. Then we plot it, and the axis command just gives us a nice version for the axis. We're just going to try to look at this part. We're going to try to look at one period. So let's take a look at the fundamental frequency here with n equal to 1. Change folder. So this is the fundamental frequency. This is the sine. This is the base sine wave that gets this to work. Then if we crank up adding some more terms, so let's say we take it out to 10 terms. So we're summing 1, 3, 5, 7, 9. It already starts to kind of look like our square wave here, right? It's really bumpy in that area there, which is what you'd expect from a sine wave. It's already starting to look like it. So let's take it out to 100 terms. And you see it gets even better. We get some problems at the points of discontinuity, right? So the function here is a straight line. So around those points you see it's bumpy and we get some ripples in the place that we want to keep it flat. But overall this is starting to look like it. So let's continue on with making this number bigger. Let's take it to 1,000 terms. And if we do that, we see that it's getting better. It's getting even more flat here. The ripples look like they've stopped a little bit. But we get this big gap here at the discontinuity, which is where you're going to see most of the problems with this happening. And so let's finally take it to 10,000 terms. And so this is as far as I'm going to take it, because at this point, with the human eye, we can't really see a difference between these two. It looks like taking it to about 10,000 terms gives us a good enough kind of looking graph. And if you wanted to approximate this with a sum of cosines, this would probably be good enough for all practical applications, probably more than good enough for any practical applications. I just want to stress that I've only taken this to 10,000 terms, so this taken to 10,000 terms is not exactly equal to this. It's very, very close, and it looks very good. But if you look at the corners here, if you look at the points of discontinuity, we see that it's 0.9 at some points, it's 0.95 at the other points, right? And it gets very quickly to something very, very close to 1, but is not exactly 1. And as we go down, it's not exactly -1. So if we look as we come down here, it shoots down very quickly, which is what we want, but we actually want that to be instantaneous. So unless we take this summation to infinity, it won't be exact. But that is how Fourier series work. This is a simple example where all of our sine terms ended up being 0. And actually, this is called the trigonometric Fourier series. You can write this as as sine and cosine, like we did here, or you can write it in terms of just cosine. In that case, it's called the compact trigonometric Fourier series. And luckily for us, this all worked out. Oh, this would actually be a sine in the end. Sorry about that. Right? We said that all of our sine terms ended up being, all of our cosine terms ended up being 0, so this had to be the sine terms. Yeah, so we could phase shift this and write it as just cosines, which is called the compact trigonometric Fourier series. Or we can use a complex exponential, and we know that complex exponentials, e to the j whatever, will give us sine and cosines, so kind of what we're looking for. And then the only caveat is that our coefficients out here will also be imaginary numbers, so that we get a pure real number when we look at the graph. And so maybe we'll do something on that later, but for right now, I just want you to be aware of it. I hope you guys learned something. I hope that the MatLab helped, and have a nice day, guys.